In this video, we will look at graphs of trigonometric functions other than sine, cosine, and tan, namely secant and cosecant. And also tan. So this is section 8.2 of the OpenStax textbook, College Algebra and Trigonometry. Let's start with the tangent function. So the general shape of the tangent function kind of looks like the cubic function, if you recall from algebra. Now, one thing that's peculiar about the tangent function graphs, which we didn't encounter in sine or cosine, is that here we are going to have what are called vertical asymptotes. So, and the reason behind that is that you will recall that the tangent function of, for example, pi over 2, tan pi over 2, is undefined. And whenever a function is undefined on the graph, you get a vertical tangent, a vertical asymptote. And then there are other values of the angles, other angles for which the function is undefined, and therefore you get more vertical asymptotes. So the graph itself so that's the first vertical asymptote at pi over 2. And then on the other side of the y-axis, you have at negative pi over 2 also a vertical asymptote. And so at both of these angles, the tan function is undefined. And the graph between the asymptotes looks like this. So it's an increasing function, kind of like the cubic function graph. And then you have more vertical asymptotes on either side. So at pi over 2, and then 3 pi over 2, and 5 pi over 2, etc. Same thing on this side, on the negative side. So that's negative 3 pi over 2. The x-intercept of the graph, this one is at the origin, and then at pi, and then negative pi. And similarly, you're going to have 0 pi, and then 3 pi, etc. 2 pi, 3 pi, 4 pi. Couple of things to note. The general form of a tangent function, the basic tangent function, is a tan bx. So there can be two constants in the function. The constant a in front of the tan function, its absolute value is called the stretching factor. That's the factor by which the graph of tan x is stretched vertically if you have a constant other than 1 in front. The range of the graph is from negative infinity to infinity. the value of the tan function can be any real numbers. Let's consider an example of this. This is problem number 22. And we have to graph tangent of pi over 2x. So the first step in graphing the tan function is to find the vertical asymptotes. And in a simple y equals tan x, the first vertical asymptote was at pi over 2. So whenever the angle or the argument of the tan function is pi over 2, you're going to have a vertical asymptote. So in this case, the argument of the tan function is pi over 2x. So you set that equal to pi over 2, and then solve for x. So there's a factor of pi over 2 on both sides. That means x equals 1. So in this graph, whenever x is 1, you're going to have a vertical asymptote. Now, if there's a vertical asymptote at 1, then there is one at -1 as well. And the graph itself between those vertical asymptotes will look like this. The problem asks for 2 periods of this function. So we need, this is 1 period, we need 1 more. So to figure out where the next vertical asymptote would be, one thing you can do is look at the distance between these 2 asymptotes. There's one -1 unit to the left and then 1 unit to the right. So the distance between them is 2. So the next one will be removed by 2 from x equals 1 vertical asymptote. So you add a 2 to that 1 and you get a 3. And then the graph itself will look like this. We also need to label the y-axis. And there, the idea is whatever the stretching factor is, in this case, the stretching factor is 1. Because that's the constant in front of tan pi over 2x. And at the quarter point between 2 successive vertical asymptotes, which would be here. And if that would be -1/2. At the quarter point, the y coordinate of the graph would be whatever the stretching factor is, the negative of that, so -1. Similarly, on the positive side, at 3/4 point or 3/4 in this case, the y coordinate of the graph would be +1. So that's the graph of tan pi over 2x. Let's look at a couple of variations of this. So if you had y equals negative tan pi over 2x, the graph would be just like the one in the previous case. The only difference will be that it'll be reflected about the x-axis. So instead of an increasing function, it'll be a decreasing function. You still have the vertical asymptote at 1 and 3 and -1. But the graph will be a decreasing function like that. And as far as the y-axis is concerned, at the 1/4 point or at -1/2, the value of the function will be 1, and at 1/2 it'll be -1. So basically the difference between a positive tan function and a negative one is the positive one. It's an increasing function like you see in this case. For a -1, it becomes a decreasing function. If you had a constant other than 1 in front, the stretching factor, let's say -3, tan pi over 2x. The only thing that will be different is the y coordinates, instead of being 1 and -1, will be 3 and -3. So this and this will change. At the 1/4 point, this would be 3, and at 3/4 point, it'll be -3. So that's how you graph the tangent function. First, figure out the vertical asymptote by setting the angle equal to pi over 2, and then a similar vertical asymptote will be found on the other side of the y-axis with a negative value. And then you find the distance between them and add that distance to the rightmost vertical asymptote, and that gives you the next vertical asymptote. Next, we will look at the cosecant function. To graph the cosecant function, we start with the graph of its reciprocal, which is sine. So a regular sine function we know looks like this. And this other period of 2 pi. And then that's pi. That's 0, -pi, and -2 pi. The amplitude of the sine function is 1, so that's 1, that's -1. Now, since cosecant is the reciprocal of sine, whenever sine x is 0, cosecant will be undefined because 1/0 is undefined. So wherever you see the x-intercepts, go ahead and make the vertical asymptotes. So at 2 pi, at pi, at 0, at negative pi, and at negative 2 pi. And then the graph of cosecant x itself, I'm going to draw in red. Goes like this. It just barely touches the peak of the sine graph. So that is the graph of cosecant x. And you can have variations on the cosecant x function. So for example, let's consider y equals 2 cosecant 3x. So we're going to start with the reciprocal of that. So 2 sine 3x. First, we need to know the period of this function. 2 pi over b. So 2 pi over 3. So the graph itself and it's a positive cosecant function or a positive sine function. So the graph looks like this. Period is 2 pi over 3. So that's 2 pi over 3. That's half of that. So pi over 3. That's 0. That's negative pi over 3. And negative 2 pi over 3. And again, wherever you have x-intercept, you make the vertical asymptote. And then you complete the graph. So that's the, and also the amplitude of the sine function was 2. So this is equal to 2 and negative 2. If it was a negative cosecant function, then you would start with the graph of negative sine function. And the rest is just exactly the same. The graph of the secant function is drawn in a similar fashion. And let me consider, say, y equals negative 5 secant of 4x. So you start with the graph of -5. The reciprocal of secant is cosine of 4x. So you need to know the period, 2 pi over b, which is 4. So that's pi over 2. Now it's a negative cosine function, so the graph begins at the bottom, goes up, and that's one period. That's another period. So that's the origin, 0. And then that's one period, so that's pi over 2. That's half of that, so pi over 4. And then that would be pi over 8. So pi over 8, 2 pi over 8, this would be 3 pi over 8. And then the same thing on the negative side. So negative pi over 8, negative pi over 4, negative 3 pi over 8, and negative pi over 2. And then you draw the vertical asymptotes at all the x-intercepts. Oh, also the amplitude is 5. So this would be 5 and -5. And then you draw the vertical asymptotes, so at the x-intercepts. And then you complete the graph, which I'm going to draw in blue. So that is the graph of -5 secant 4x. Next, we will look at the graph of the cotangent function. Let's suppose f of x equals 4 cotangent of 5x. Now, again, the first thing to do is to find the vertical asymptote. And for the cotangent function, you need to set the argument of the function, or the angle, equal to 0 and pi. Because those are the angles for which the cotangent is undefined. So vertical asymptote at 5x equals 0, which means x is 0. And then 5x equals pi, which means x equals, 5x, not 5, which means x equals pi over 5. So you draw your axes. With a vertical asymptote at 0. And then at pi over 5, and negative pi over 5 also. The graph of the cotangent function is a decreasing function. So it's going to go like this. The x-intercept in this case will be at midway between 0 and pi over 5, so pi over 10, and negative pi over 10. And then in terms of labeling the y-axis, at the at the 1/4 point between two successive vertical asymptotes, the value of the function is equal to the stretching factor, which in this case is 4. So halfway between pi over 10 and 0 would be pi over 20. So you go up to the graph, and then you turn towards the y-axis, and that's equal to 4. And then on the other side, at this is pi over 20. On the other side, at negative pi over 20, the value would be negative 4. So that's the graph of 4 cotangent of pi x. If it was a negative cotangent function, the only difference would be that the graph would be an increasing function rather than decreasing. So it'll look like this. Let's look at problem number 39 in the book, where in the next two problems, we'll look at a given graph and try to write down the function of that graph. So let's go to the textbook. So problem 39. For the following exercises, we have to find an equation for the graph of each function. So let's first observe a few properties of this graph. First of all, it has a vertical asymptote. it has a vertical asymptote at the y-axis at x equals 0. So VA at x equals 0. And that tells us that it's a cosecant function because sine of 0 is 0. If sine of 0 is 0, then the cosecant function there would be undefined. So it's a cosecant function. That's one thing we know right away. And then the amplitude of the sine function, you just have to look at the bottom of that curve and the top of that curve. And they seem to have y coordinates of 1 and -1. So the amplitude is 1. And then the period is basically the distance from here to here. That's one period. And that distance is pi, because they tell you that this vertical asymptote is pi over 2, and that's like at half the period. So the distance from here to here, this would be pi. So the period is pi, and period is 2 pi over b. So that means b is 2. So amplitude is 1, b is 2. So the function that we see here is y equals 1 times cosecant of 2x. That's the equation of that graph. Let's look at one last problem. This is number 40. Same thing, we have to find the equation for this. Now, notice that this has a vertical asymptote at x equals 0 also. You just look at the shape of the curve as it's approaching the y-axis. So, it seems obvious that there is a vertical asymptote there. And a vertical asymptote, just by looking at it, it's either a tan or a cotan function. A vertical asymptote at x equals 0 is the property of the cotangent function. So it's a cotangent function. At the quarter point between these two asymptotes, which would be here, the y coordinate seems to be about 1. And then at the 3/4 point, which would be over here, the y coordinate is about -1. So the stretching factor is 1. The period of the function basically, the distance between these two vertical asymptotes is equal to 1, because that's the x-coordinate of here. The x-coordinate for this vertical asymptote is 0, so the period is 1. And that means b, for the cotangent function or the tangent function, the period is pi over b, which means b is pi over the period, or pi over 1 in this case. So b is pi, stretching factor is 1, and it's a cotangent function. So we can conclude that f of x equals 1 times cotangent of pi x. That's your answer. And that brings us to the end of this video.